In this video, I'm going to draw the finite state machine from the high-level state machine. So if you take a look at your high-level state machine, you see that you have two states. That does not change. So begin with drawing your two states. My finite state machine is down here. So I have state S, state T, and remember, you can accomplish two states with a single bit encoding. So this would be considered state 0, and this would be considered state 1. The next thing to do is to put the same transition lines that you have, right? Our labels will change, but write out and draw out the same transition lines. So I have a transition line that stays in S, right? I have one moving over to T, I have one moving back to S, and I have one that stays in T. So now write out the conditions for your transition lines. And the condition E greater than 6 becomes a flag, because if you notice from your data path, right, this greater than value is just a flag, a 0 or a 1. E is either greater than 6 or it's not, right? So it's a single bit flag. So write it as a variable that represents that flag. So here, not E greater than 6 is written as the flag name. So we're just labeling these E underscore GT underscore 6 with the complement notation, right? The little tick mark. And then movement from S to T is a true for E underscore GT underscore 6. Staying inside T is the same, right? That flag is true again. E underscore GT underscore 6. And then movement from T back to S on the complement of the flag. So at this point, you have the finite state machine mostly drawn. What you need to focus on next are these values for I and Z. What changes in the finite state machine is that these values become flags, right? What does my value on my S line need to be to make I a 0? What does my value on my S line need to be to make Z a 0? That's what is being replaced here. So the variables that we're using in our finite state machine are I underscore S for the S's mux input, I underscore load for I's register load input, Z underscore S for Z's mux, and Z underscore load for Z's register. So these four values are control bits that are outputs from the controller inputs into the data path. And that's what gets determined by the combinational logic that we're going to come up with next. So take a look at I's value of 0, right? And so I'm in I's mux. I0 is on the 1 line, so S would be a 1. Load is always 1 because the only time the register is going to load is when load is 1. Z0 is on my 1 line as well, so that would go there. And then a 1 for load as well. Again, register load value is always 1. Now, same thing for this set here. So when is I equal to I plus 2? Look at that line on the mux, and that's at value 0 for S. Load is 1. Z equals I is on the 0 line. Load is 1. So you have your four values there. Now you can move on to your state table.